First pictures now coming in from Puerto Rico after taking a direct hit. Hurricane Maria slamming into the island, and as you heard, one official saying the island is destroyed.
Hi, my name is Brandon Raguz, and today I'll be talking about everything you need to know about hurricanes, what they are, how they come to be, and just the forces that provide the power for them to be so destructive. This is just a quick animation of the Hurricane Katrina as it makes landfall over New Orleans in 2005. So first off, what is a hurricane? A hurricane is actually a large cyclonic storm. It's a collection of thunderstorms in a cyclone shape with winds that have to be over 74 miles per hour to be classified as a storm, and it's formed over warm waters in the ocean. They are predictable to an extent. There are models and methods to predict how big it'll be, how strong the winds will be, and where it will go, but they are still very dangerous. These storms are powered by the latent heat of the ocean, and the winds alone are enough to damage buildings, and the wind speeds are how the storms are actually categorized. So getting into categorization, the Saffir-Simpson scale is the method in which hurricanes are categorized. It's a 5-step scale, so category 1, 2, 3, 4, and 5, with 3 through 5 being the major hurricanes. So as you can see, actually, I don't want the pen, I want the laser pointer. You can see here the wind speeds are what truly categorizes the scales, and then over here is just a description of how they are, how damaging they can be. So category 1 has 74 to 95 mile per hour winds, and they are dangerous and they can produce some damage. And then category 2 has 96 to 110 mile per hour winds, which these winds are extremely dangerous and can cause extensive damage. And then category 3, getting into the major hurricanes, which are very devastating, have 111 to 129 mile per hour winds, and these can destroy some well-built homes, and electricity and water will be knocked out. Category 4 has 130 to 156 mile per hour winds, which this is catastrophic damage and definitely massive devastation across the hurricane's path. Category 5, the biggest, has 157 mile per hour or higher winds, which is utter destruction as it passes over its path and will destroy homes, will take out power for weeks. So wind speed is talked about a lot with hurricanes. So real quick, just how to measure wind speed. It's actually measured 10 meters above the water's surface, and has to be measured for an average of 1 minute in order for it to be considered an average wind speed. So here's a quick video.
When it comes to hurricanes, each one's impacts are a little bit different, but the wind speeds that we talk about along the Saffir-Simpson scale, those are very specific, and the damage caused in those categories, kind of predictable. So let me show you. Let's start off with a Category 1 storm. And the damage here, not too bad. A couple of shingles fall off, you can have some palm fronds bending in the wind, but everything basically remains intact. Category 2, that's where you really start to feel it. Look at the windows of the house. They can be hit from debris from the outside and already start breaking in a Category 2. Your trees are significantly bent over in the wind, and the siding of the house itself can break, flapping there in the wind, adding to those eerie noises inside. Category 3. I've heard only a Category 3, but it's not only anything except really bad news. In a Category 3, you can have the door of the house blown in because the winds get so strong. You can have the roof of the house with the flap up and down in the wind because it can lift off those weak points, and a lot of those trees start to fall. Category 4, damage is even worse. You get most trees falling, most of your windows breaking, most of your shingles fly away, and then Cat 5 is as high as the category scale goes. By Cat 5, no shingles remain anywhere nearby. The holes in the roof get so big that the walls of the house start to fall because they're not attached to anything anymore. There won't be any trees up in the neighborhood. That's just catastrophic damage. Again, that's just from the wind. There are other impacts from hurricanes, and they all vary through the season. So stick with the Weather Channel to keep you safe from the tropics that change your neck.
So moving from categorizing hurricanes, we get into naming hurricanes. And actually, hurricanes are only called hurricanes in the Atlantic, and they only occur on the western boundary of the Atlantic. Typhoons are what they are called. These tropical cyclones are called on the western boundary of the Pacific Ocean, and then they are just called tropical cyclones in the Indian Ocean and the southern hemisphere. So when it comes to actually naming them, like Hurricane Katrina, Hurricane Irma, Harvey, Matthew, all those, the World Meteorological Organization keeps a recycled 6-year list. So every 6 years, it goes back. So 2017's list will be used again in 2023. So these lists of names are maintained through a very strict procedure, and the names actually can be retired based on how deadly or how inappropriate the use of the name would be. So all of the hurricanes from 2017 are actually being retired because of how deadly they were. So Irma, Harvey, Jose, they will not be used anymore. This committee will be coming up with new names to replace those. So getting into the general structure of a hurricane, there's three main parts: the eye wall, and the rain bands. The eye is the center of the storm with actually the least storm-like conditions, so it can be actually clear, like clear skies. You can have very minimal winds, very little rain, and then you move right to the eye wall, which is actually the ringest thunderstorms around the eye, where the winds and the rainfall are the heaviest and most dangerous. So this is where most of the damage from the thunderstorms comes from. And then outside of that, you have the rain bands, which is hundreds of miles of rain clouds and thunderstorm clouds. And these can, like I said, these can span for hundreds of miles. And Hurricane Sandy was actually one of the biggest, in terms of size, hurricanes to exist, with the rain bands extending out past 1,000 miles. And this is just a quick image of the anatomy of a hurricane. So as you can see, you have the eye in the center where it almost looks like a little funnel or an eye, and then you have the eye wall next to it, which is a very thick band of thunderstorms. And then as you go around that, you have your rain bands that extend out from the storm. And you can see here it shows that the storm is rotating in a counterclockwise direction, which actually indicates it would be in the northern hemisphere, as stated up here. So the formation of a hurricane actually starts as a tropical disturbance over further into the eastern boundary of the Atlantic Ocean. We'll be talking about the Atlantic Ocean for this for now. And then, so a tropical disturbance is a tropical weather system of convection originating in the tropics, remaining for at least 24 hours. So it's not cyclonic at the moment, but it is still a disturbance of the atmosphere. And then as it begins to evolve, it evolves into a tropical depression, as you can see here. And this is a cyclone. It becomes a cyclone at this moment, and it is a closed circulation and has a max wind speed of 38 miles per hour. The wind speed is important because that's how they separate the depression from the storm, from the hurricane. And then as we continue on, it becomes a tropical storm. This is when wind speed starts to increase. You get above 39 miles per hour, but lower than 73. And the convection is starting to concentrate near the center of the cyclone. And then finally it becomes a hurricane once the wind speeds exceed 74 miles per hour. So we'll get into now how these hurricanes are actually formed. So they are formed from a cyclone that actually grows with the warmth of the ocean waters. So when the waters are above 26.5 degrees C to an ocean depth of 45 meters, the storm activity in the cyclone will build. And this is because when the core of the storm begins to shift from cold to warm, it is beginning to get its energy from latent heat, which is extremely important. And as the wind speeds increase and the moisture level grows, latent heat continues to build in there and allow it to get more fuel for the storm. So the storm begins to grow. And then another need for the storm is it actually needs weak winds atop the storm to allow for this disturbance in the pressure system around the storm. And then it also needs a Coriolis effect to create the cyclonic effect. What is the Coriolis effect, you might ask? Actually, it is the deflection of circulating air due to Earth's rotation. So as air is not connected to the Earth and the Earth rotates underneath it, it seems like it's deflecting, but really it's still traveling in a straight path. But in relation to the Earth, it is deflecting. So this is what causes hurricanes to rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. As you can see in the diagram here, you can see a the intended path of something in the northern hemisphere to be going straight up, but as the Earth rotates, it is deflected to the right. But then in the southern hemisphere, as it's going down towards the pole, it's deflected to the left. So the reason why hurricanes rotate counterclockwise in the northern hemisphere is because when Coriolis takes effect and causes the winds to rotate to the right, or deflect to the right, should I say, um, the storm rotates in the opposite direction of the deflection, so it is rotating counterclockwise if the wind's coming off to the right. So in the southern hemisphere, it's the opposite, and it rotates clockwise. So actually near the equator, the Coriolis effect begins to weaken, as you can see with this. So it's next to nothing near the equator, and at the equator it is non-existent in general. So cyclones and hurricanes cannot form at the equator, and neither can they cross the equator. So now latent heat. This is amazing. Latent heat is the heat released by water vapor that has been evaporated from the ocean and condenses. So why is latent heat amazing? Because it's the fuel that fuels hurricanes. So as the surrounding atmosphere warms up and the warm air begins to take up more space than the cold air, then this warm air moves away from the center of the storm, thus decreasing the surface air pressure down here, allowing more air to come towards the center of the storm, bringing more warm water to the center of the storm. So this creates a large pressure gradient at the center of the storm, drawing more warm, moist air rising from the ocean's surface and further fueling the storm. So as long as the warm ocean is present, this is a continuous cycle. So it will keep going and going and going until it reaches, land or colder waters. So storm surge was mentioned in the short video, but it's a huge impact on land as the hurricane begins to hit, and it's the rapid rising of waters due to high winds blowing these waters towards the shore. And then a small portion of this surge is driven by decreased surface pressure from the, as you can see in the diagram, on latent heat, but the majority of it has to do with the high winds blowing this water towards the shore. So the ocean side of the storm surge is minimal because all the water is allowed to flow away from the storm, but on the opposite side, it begins to build up when it gets near the coast. So it creates more storm surge on the coastal side. So then this is actually the cause for most of the damage in low-lying areas. So these factors affecting storm surge, storm intensity and size are huge factors. They're extremely sensitive to this, as well as storm forward speed. So the faster a storm is moving forward, the faster the storm surge will affect the coast. And then the approach angle to the coast is another big factor. So other important aspects of hurricanes is, one simple thing is hurricanes season begins the beginning of June and ends in November. But though these hurricanes can occur outside of the season and have before, and then they almost always travel towards the poles, or at least in a northern or southern direction, depending on the hemisphere in which they're in. And then climate change and global warming is actually having a huge impact on these storms. So the question presents itself, how does climate change affect hurricanes? NOAA states that anthropogenic warming will likely cause global tropical cyclones to be more intense by the end of the century. But while global warming may decrease the temperature difference between the poles and the equator, as the poles start to become warmer and the air becomes more humid, this will consequently decrease the number of storms that occur. But this warming climate could actually will lead to an increase in water vapor in the air, which would then increase the intensity and the occurrence of more intense tropical storms and hurricanes. So while the general occurrence of storms, like average storms, will decrease due to the lower difference. The intense storms, the ones that are more damaging and will cost more and will take more lives, could actually increase because once they start and the warmer ocean temperatures will just add more fuel. There will be more fuel available and it will just grow bigger and bigger, and we'll get storms that are closer to Harvey. We'll get storms like Irma and Jose and Hurricane Sandy. So then there's the other effects of climate change on hurricanes. So the melting glaciers and ice caps will cause sea levels to rise, which will then cause storm surge and flooding from hurricanes to be even more devastating. So as the mean sea level rises, it will the baseline for the storm surge to build off of will be higher, and then it will cause flooding to go deep or further inland, causing more damage to structures, buildings, houses, and people. And then as ocean temperatures rise, there's actually less cold water below the surface to weaken hurricanes. So one of the reasons why Harvey was so devastating was actually, yeah, sorry, one of the reasons why Katrina was so devastating was it hit these warm spots, like deep, warm pools of water in the Gulf of Mexico, which caused it to just keep increasing rather than catching cold areas and weakening a little bit. So there's least as cold water decreases below the surface, then storms won't actually weaken when they go over them and when the winds blow warm water away from the surface, allowing colder water to come up. It'll just be warm water underneath. But there is actually a possibility that climate change could have a negative effect on hurricanes, and this is that there's a chance it could increase vertical wind shear in the upper atmosphere, which would then blow off the top of hurricanes and storms, causing them to weaken and not allowing them to occur as easily. So on the side of this, there's a little picture that Climate Council put out about how climate change made Hurricane Matthew worse. First one was that warmer oceans caused stronger storms. So Matthew had the highest cyclone energy of any storm in the Caribbean up to that point. And then warmer oceans cause heavier rains. So more rains, more flooding, more everything will cause more damage as the hurricane hits. And then the higher sea levels, like I said, would cause increased storm surge, more flooding, and will cause lower lying areas to be more at risk. So then Hurricane Harvey, as I said, was considered to be as bad as it was because of climate change, and it produced an unprecedented amount of rainfall. And the National Weather Service put this out that they had to update their color charts on their graphics in order to effectively map it. So on the left, you can see the center of the storm or the rainfall area is all like a dark purple, but then when they updated it, they added a lighter purple and a white to show that there was even more rain than they could map with their previous colors. So then another interesting question comes up is how does El Nino and other oscillation patterns affect hurricanes? So El Nino is just the occurrence of warmer waters moving eastward in the Pacific due to weakened trade winds and winds over the equator. So this actually causes Atlantic hurricanes to be suppressed, and hurricanes are less likely to make land, but it can increase the risk of typhoons in some parts of Asia. So now we get on the question, how does a hurricane die? It's actually just the lack of fuel that causes a hurricane to weaken and die. So warm water is the fuel for hurricanes, as I've said previously. And when it moves over land or cooler waters, the storm weakens. So obviously when it goes over land, there's no latent heat of evaporation from the ocean to power it. So the center of the storm doesn't get that power. It's just running off itself and it just fizzles out. But then once it goes over cool waters, or if it goes over cool waters, it can actually, the latent heat isn't there either. So it doesn't have the fuel it needs. And one of the interesting things is that the winds of the storm actually stir up ocean waters, and the cyclonic winds cause Ekman transport, and the surface waters diverge under the storm. So Ekman transport is the net motion of water as a result of friction between wind and surface waters, as well as the different layers of water. So a wind going eastward the net Ekman transport will actually have the underlying waters going south. And this causes cold waters to be brought to the surface through upwelling as the surface waters diverge from the center of the storm. So then that also leads into weakening the storm and making it die. But upwelling brings up an interesting point that hurricanes can actually cause increased production or enhanced production. Well, because of the divergence of water under the storm as the system's dying, the colder nutrient-rich waters are upwelled. So upwelling is the process of the warmer surface waters being pushed away by winds and wind friction, and the colder nutrient-rich waters rising up to fill up that space that the lack of warm water left. So a study done at Johns Hopkins University in 2004 showed that satellite imagery increased chlorophyll construction within the cool water wake of 13 hurricanes of the Sargasso Sea. So this means that as these 13 hurricanes passed over the Sargasso Sea in the Atlantic, the cold water wake left behind them was actually had increased levels of chlorophyll. So there was more chlorophyll in the water as the cold water brought it up from deeper depths. And this means there's increased production, and it, like Dr. Oakley would say, we can measure the ocean from space. So that's it. These are citations of the first slide's pictures, and then these are my references. And I just thank you for listening in on this, and hope you enjoyed and learned a lot about hurricanes.